Hello everyone, and welcome to recitation number 6. Reminder, we have an offline recitation 5 where we go over cardinality. But for today, it's gonna be all about induction. So hopefully by the end of this session, you'll know pretty much everything you need. So we'll be covering simple induction, or just induction, and strong induction. I really hope that you'll both be able to know how to use each one of these, obviously, and when to use them. Like, when should you use strong induction? When should you use simple induction? Okay. With that, after this is finished, we'd have covered every idea that you have for the exam. Induction, sets, functions, cardinality, everything. So it's really time for you to study from now till Monday, because Monday we're going to be reviewing assignment 5, I believe. So you have time to revise everything and ask me then if you have any questions. But that's for Monday. As for right now, for this hour, let's try and understand induction. Now, both of these are gonna go the same way. We have 3 steps for using induction. First, we have the base case. That's where whatever we're trying to prove, we prove it for a specific case. So if they're saying prove this is blah, blah, blah for n is greater than or equal to something, like 5, you'd say, okay, just let n equal 5 and prove that whatever we're trying to do is true. And that would be enough. You can just do one case, or you can also try to do a couple of cases extra, just so you get an idea. Like, the more cases you do, the more whatever pattern happens is going to be more apparent. So that's the base case. Then you have your induction hypotheses. This is where it's just simply a statement where you say, assume that whatever we're trying to prove is true for n. Assume that the statement is true. That's it. That's all you do. For n, there's a lot of different ways to do this. You can either say prove that it's equal for n, or prove that it's equal for n equals k. I'll try to do all the different cases. So hypotheses, assume it is true for n, and then the third step which is the induction step. It's here where you try to prove it for the next step, which is for n plus 1. If you had said for n, or if you said let n equals k, you try to prove it for n equals k plus 1. Like, for the next step, this is just different ways of symbolizing it. So that's simple. What's the difference between it and strong induction? It's just gonna be the inductive step. So here, step 1 and step 3 are gonna be exactly the same. The difference is here, instead of assuming it's only true for n, you'd assume it's true up to n. Like, this is saying it's only true for n is k. Here saying it's true up to n equals k. So like, you're assuming, hey, for n equals your minimum, like let's say 5, 6, 7, etc., all the way up to k, this is all true. You just want to prove it for k plus 1. You might ask, hey, why don't I always use then strong induction? Because it seems like, hey, they're doing the same thing. Why don't I just ease my mind and always use strong induction? Like, assume everything up to k, up to n or up to k is true. Well, You could do that, but it's not necessary. On paper, it's not going to make much of a difference because you're only saying one word. You're saying, hey, here up to n, where over here you're saying for n. Difference is in words. But if you actually want to apply this, like in an actual programming sense, in strong induction, you need more resources. Like you're saying, I need n equals 5, 6, 7, all the way up to k. You need more resources. Whereas in the simple induction, you're saying, I only need n equals k. So of course, if you're gonna need more resources, you're gonna have to pay for them, for example, in terms of time, in terms of complexity, and all that. Whew. Simplest way to understand this stuff is to actually solve. So prove that 5 power n plus 3 is divisible by 4 for all positive integers. I'll do this first one with you. So simple. Usually we're gonna tell you when to use simple or strong. If it's not mentioned, then that's probably going to mean it's simple induction. So step 1 is our base case. We want to prove that this is true for all positive integers. So for all n greater than or equal to 0. Well, let's try a case. N is 0. What happens then? So you say for n is 0, you get 5 power 0 plus 3. 5 power 0 is 1 plus 3, that's 4. And done. 4 is definitely divisible by 4. You can try a few other cases like we said. So 5 power 1 plus 3, that's going to be 8, also divisible by 4, and so on. That's the base case. Now, the induction hypotheses, like we said, this is just a statement you have to say every time. Assume it's true for, let's say, this time n equals k. Induction step. Let's prove for n equals k plus 1. So we assume that this property is true for k. Then that means like 5 power k plus 3 is divisible by 4. So this is just your given right now. So this is like, remember rules of inference if you want to relate it to that, sort of. This is now given, it's true. 5 power k plus 3 is divisible by 4. You just have to prove it now for this. We have to now prove that 5 power k plus 1 plus 3 is divisible by 4. How can we do that? Well, you want this to appear in what you're trying to prove. Your given is 5 power k plus 3 is divisible by 4. You want to make use of that given in order to solve the problem. Well, plus 3 is already here, so that part is sort of done. You want now to see 5 power k. But we have 5 power k plus 1. Well, let's just break that down. What is 5 power k plus 1? It's just 5 times 5 power k. We have r plus 3 here. So now we can sort of see it. We just want to kind of get rid of this other 5. But what is this other 5? It's just saying 5 times 5 power k. So it's like 5 power k plus 5 power k plus 5 power k 5 times. Or in other words, it's 4 times 5 power k plus 1 5 power k on its own, plus 3. Hopefully you already see that it's over now, because this is our given. We know that 5 power k plus 3 is divisible by 4. So we can just write, for example, it's equivalent to 4m, like 4 times something, where m is an integer. What about the other side? It's already 4 times something. 4 times 5 power k. So if you just take 4 in common into 5k plus m, you're done. It's 4 times something. So add this whole thing is divisible by 4. Okay. Any questions so far about simple induction? Okay. Let's try one more with a different idea. Consider the following recursive definition of a function. F of 1 equals 1. F of n is 2 times f of n minus 1 plus 1. Why is it recursive? Because it's related to its previous part. Like f power n, what you're trying to, the element you're trying to calculate right now, is related to its previous element. Kind of like a sequence. But they don't want that. They're saying find a non-recursive definition for f and prove by induction that this definition is correct. So actually, we have to give a definition for f of n that's not recursive. How can we do that? Well, let's try some n's. We know that f of 1 is 1 because it's given. What about f of 2? It's 2 times f of 1 plus 1, which is 3. Okay, keep going. It's still not clear. F power 3 is 2 times f power 2. Sorry, it's not f power 2 or f power 1. It's just f of 1, f of 2 plus 1. So 2 times 3 plus 1, that's a 7. One more just for fun. F of 4, 2 times f of 3, which is 7 plus 1. So that's 15. Does anybody have an idea what this function is? Can you give me a non-recursive definition? Like by non-recursive definition, what I mean is, hey, tell me that f of n is, I don't know, 3n plus 16. It's not that, but something like this. Like f of n is something. Not recursively like this, where it's related to its previous element. Yes, you want to conclude it from these examples that we just did, and then you prove it using induction. Okay, someone is saying 7 is equal to 2 times 3 plus 1. Okay, what about 15? It's 2 times 7 plus 1. So how did we jump from 2 times 3 to 2 times 7? Yes, f of 3 is that. Yeah, here you're using, no, you want an entirely different thing. A hint, it has to do with power. Like, it's almost 2 power n, right? It's almost 2 power n. Because what's 2 power 2, for example? It's 4. What's 2 power 3? It's 8. What's 2 power 4? It's 16. What's 2 power 1? It's 2. Like it's almost every time 2 power something, but just short of that by 1. Exactly, it's 2 power n, and then we have a minus 1 next to it. That's what it seems to be. Like f of 5, it's 2 times 15, which is 30, plus 1 gives us 31. And we know that 2 power 5 is 32, just short of that. Okay. So now we have our non-recursive definition. We want to prove it by induction. Okay. Now we want to prove that this is actually the same as this. So what we do is, let's assume we have, let's define f prime, a new mapping from n to n, such that n goes to 2 power n minus 1. Okay, so this is basically just saying that f of n equals 2 power n minus 1. Okay, now we wanna prove our induction hypothesis, which is, for example, p of n. So kind of like predicates, you say p of n, and what is your statement? We just want to prove that, hey, f of n is the same as f of n. This isn't the derivative, this is just like another function. Let's actually call it f1, so we don't get confused.
The function is repeating itself, but in another way. So
What are you saying?
the function is repeating itself, but in another way.
What do you mean it's repeating itself?
The same function that before. We're using that same term before.
You mean yeah, exactly. This is what recursive means. Like it's repeating itself. It's always using the previous element. And
Yeah.
the question is saying, no, find a non-recursive definition. We
Mm-hmm.
did, which is this 2 power n minus 1. This isn't repeating itself. This isn't recursing itself. It doesn't have to
Oh,
do with its previous element. But
yeah.
now we have to prove that it's actually the same function. Like we have to say that 2 power n minus 1 is actually the same as this recursive definition.
Mm-hmm.
And how? Using this statement that I just wrote. We're going to prove that f of n equals f1, like the new function of n, for every n greater than or equal to 1. If we do that, then yes, we prove that they're the same for every element possible. Okay? So let's do that. Now it's just the normal induction that we know. So base case. Base case is already done because you can just say, hey, f of 1 is 2 power 0 minus 1. So 2 minus 1 equals 1. Sorry, this is f1 of 1, which equals f of 1, this thing here. So f1 equals 1, that's what they said. And our function that we just made is the same thing for 1. Induction hypotheses, you know it. We'll just assume it's true up to n. So assume p of n, our predicate, is true up to n. Induction hypotheses. Now let's prove it for the induction step, which says prove for n plus 1. So what is that? So now how can we actually prove it? Well, what's f1 of n plus 1? It's going to be 2 power n plus 1 minus 1. What about the other side? Okay, so this is what we're saying. Our function is saying this is what it's gonna be. It's gonna be 2 power n plus 1 minus 1. Well, gonna new. Let me just need to add a new space here. Okay. So the normal f that they gave us, f of n, we're assuming that f of n is gonna equal f1 of n. Remember, this is our hypothesis. We're assuming that this is true, so that means that f of n does equal 2 power n minus 1, because it's for n. We want to prove now for n plus 1. So prove that fn of plus 1 equals what we just said, 2 power n plus 1 minus 1. So this is required to prove. How can we do that? Well, what's the definition that they gave us? This element is what? 2 times the previous element plus 1. So it's going to be 2 times f of n minus 1. This is our given. This is our assumption that f of n does equal f1 of n. So it equals 2 into 2 power n minus 1. Sorry, this is a plus 1 by their definition. So this is their definition. This is our assumption. And we have our plus 1. Let's expand and see what happens. Equals 2 n plus 1, because 2 times 2 minus 2 plus 1 minus 1. Does everybody see why this is over? Why is this done? No, we don't need strong induction for this because we just solved it using simple induction. So okay. Let me recap what we just did. Step 1, we wanted to find a non-recursive definition for f. Well, we tried some elements, and we got that, hey, f of n equals 2 power n minus 1. Okay, good. So we just simply defined this mapping right here as such. So this is just defining f of 1 to equal 2 power n minus 1. Now we have to prove this predicate, which is saying that f of n equals f1 of n for every n greater than or equal to 1. Base case was simple enough. They both equal 1. This was our hypotheses. We assumed that f of n equals 2 power n minus 1. Like, yes, it does equal f1 of n. Now we just want to prove that fn plus 1 does equal f1 of n plus 1, which is this. To do that, we applied the definition of f that they gave us. This thing right here. 2 times the previous plus 1. So fn plus 1 equals 2 times f of n, the previous, plus 1. Our hypothesis says we can do this. We expand, and we get what we're trying to find. Okay. So that's that. If you have any questions, let me know. Otherwise, try to do this one. So you want to prove that n factorial is strictly less than n power n for any n that's strictly greater than 1. So your base case should start with n equals 2. And by the way, you only need simple induction here as well. No strong induction just yet. So Reem, you're saying n is less than 2 power n? N is less than 2 power n? So n factorial is less than 2 power n, which is less than n factorial.
We make n plus 1 times n factorial. By that we can.
Mm. Yes, that's sort of what I want to do. So Reem, I'm not sure, I'll check your method in a second, but I'm not very optimistic about it. But hopefully what you want to do is somewhere you're going to have n plus 1 factorial. And I don't know if you don't already know this, but n factorial is just the n times n minus 1 times n minus 2, and so on. So n plus 1 factorial is simply n plus 1 times n factorial. So this is like this is what you want to do, and you have this as your hypotheses. You know that this is less than n, and that's how you keep going. Well, let's do this, and I'll check what you're saying, Reem. Let's do the solution. So base case n is 2. Let's prove that. N 2 factorial is just 2 times 1 equals 2. Sorry. 2 power 2 is just 4, so it's true. 2 factorial, which is 2, is less than 2 power 2, which is 4. So that's the base case. Inductive hypotheses. Assume that this is true. So if you can name this again like P of n. Like the predicate is simply saying n factorial is less than n power n. So we proved it for P of 2. Now we're going to say assume P of n is true. And we want to do the inductive step, which is prove P of n plus 1 is true. If you've noticed, sometimes I'm saying like now P of n is true. Before I was saying n for n is, where is it? So before we're saying for n equals k plus 1. Even before that, for n equals k. Like I'm trying to show you there's a lot of way of saying this, so no matter how you read it, but it all means the same thing. You're basically saying, hey, n is true, now we want to prove for n plus 1. So don't get worked out on that, because some students usually get confused by it. Let's prove that P of n plus 1 is true. So what's P of n plus 1? It's saying n factorial, n plus 1 factorial is gonna be less than, is this less than n plus 1 power n plus 1. Okay, so start with the left side, n plus 1 factorial. Like we said, it's gonna be less than, or sorry, let's say equals n plus 1 times n factorial. Well, we know that P of n is true, so n factorial is less than n power n. So this is like this, less than n plus 1 times n power n. You were right. If you're trying to prove this in the exam, you simply say by hypotheses, like by what we're assuming. Now, how can we say that this is less than this? How can we do that? Well, you already here have n plus 1. If only this was n plus 1 too, then you can add the powers and you're done. Well, is that true? Can we say that this is less than n plus 1 times n plus 1 power n? Like, is it true? Can I add a 1 to this n inside here? Yes, it is true. Why? Well, I won't go too much into the details, but this is like binomial theorem. Like if you have a plus b power k, like power something, if you want to expand this, you're going to have a power k somewhere, then you add everything in the middle, then you have b power k. Kind of like if you have a plus b squared, it's a squared plus the stuff in the middle, which is 2 times a times b, plus b squared. So when I say n plus 1 power n, if you want to expand that, you're going to have n power n plus some stuff. So n plus 1 power n is definitely greater than n power n. Which is why we can say, yes, this is less than this. But we're done now because you can say equals n plus 1 power n plus 1, which is what we're trying to prove. This is p of n plus 1. We just started from the left-hand side, less than, we reached the right-hand side. So it is true. Check this and let me know if you have any problems while I read what Dream was saying. Yeah, exactly. You were trying to do it in a calculus way or in like the in function increases faster than the other. So I'm not sure if what you said was true, but it might have been right, but we wanted to do it in an induction way. Okay. Yeah, this seems better because, yeah, okay, great. So moving on. One more question. Take a couple of minutes to try to do this, but what we're trying to prove here, show that any wire, which is exactly x inches, or x unit of measurement, such that x is a natural number and it's greater than 12, can be cut down into some pieces, each of which is exactly 4 inches or 5 inches long. So you have this, let's say it's a wire which is 12 inches. Can you cut it down into pieces which are exactly either 4 or 5? This one is yes. I think we can simply cut it into 3 4-inch parts. Okay. So this question, like in other words, what is it saying? Actually, before that, let's see what 13 is. 13, I think we can cut it into a 4, and then a 5. Okay, so 8 plus 5, that's 13. You can imagine 14, like you're going to add another one. So you would add it to either this one or this one. So 4, 5, 5. 15 obviously is just 3 times 5, so you add it here. 5, 5, 5. So what is this question saying? Any x, which is a natural number, like any n, can you break it down into 4 times something plus 5 times something for any AB that are in, I want to say z, but since they said that x is a positive number, then they probably should be in the naturals. Okay, so remember, you have a and b are naturals, and you have n is at least 12. This is another way of stating the problem. For this stuff, can you prove using induction? So 2 minutes and we'll see what we can do. Okay, let's see how we can do this. I got to how to solve it, but it's still having problem with how to write it down. Okay, let's see if I can help with that. Well, remember, if we want, let's try to use our usual step. So we've already done it for 12, 13, 14, 15. Now let's try to, so like we did a bunch of base cases. Induction hypotheses. Assume that P of n is true. What's P of n true? It's this. So yes, for n, you can find an a and b such that n equals 4a plus 5b. Now, let's try to do it for P of n plus 1. So what's P of n? Like, for n plus 1, can you break it down into 4a plus 5b? So like, can you find some a and some b here? So I'm reading some of what you're saying, 4a plus 5b. Then you said you tried to break this 5 into a 4 and a 1. No, I don't think that's gonna be the way. Okay. Well, when I look at this, I'm gonna scratch my head a lot because seriously, I can't find a way to think through this. Like we do know that P of n is true. So we do know that, hey, P of n, we know that n can be written as 4a plus 5b. So the best thing from here is, hey, add 1 to each side. So you get that n plus 1 equals 4a plus 5b plus 1. Can you do then something here? No. Like, hopefully what you want to do is have here plus 4 or plus 5, something that you can take in common with either the A or the B. That way you're done. You have 4 times something plus 5 times something. So, but if you only say simple induction, like if we only have P of n is true, that's not going to be enough. That's not going to be enough. So this is our first problem where we're actually going to be needing strong induction. So we're simply going to say in our induction hypotheses, simply that P of n is true up to n. Okay, so like now everything before, like everything between, let's say, okay, everything between 12, because remember it's for at least for x is greater than or equal to 12, less than n, everything here, then P of k is going to be true. Now we want to prove P of n plus 1 is true. Well, let's use the fact that we have Pn minus 3. Remember, I wanna see a 4 on the other side. Well, P of n minus 3 is definitely gonna be in this range, right? Well, what does this say? It says, hey, n minus 3, yes, you can find some A and some B such that this works, such that yes, n minus 3, you can write it in this form. Can anybody guess what's the next step that I want to do? Remember, we want to prove that n plus 1 has its own A and its own B. Like, what's the difference between this and this? Any guesses? So this is given, this is true. This is required to prove. And these A's and B's don't necessarily have to be the same, obviously. Well, I'll start with my given. I have that this is a true, this is a valid equation. I'm just going to add 4 on each side. Add 4 here and add 4 here. What do I get? N minus 1, n minus 3 plus 4 is 4a plus 5b plus 4. This becomes n plus 1. And over there, I'm going to take 4 in common. A plus 1 plus 5b. And that's it. You're done. You were able to find an A and a B. So 4a prime plus 5b. You were able to find an A and a B such that you can break n plus 1 into it. But the fact is, like, P of n was not enough. P of n was saying n equals 4a plus 5b. P of n minus 1, same thing. N minus 1 equals 4a plus 5b. Not enough. We had to go all the way back to n minus 3 so that when I add plus 4 on each side, I get on the left-hand side n plus 1, which is what I want. And on the right-hand side, it gets fixed. It could have also worked for P of n minus 4. Let's check that. You'd have n minus 4 equals some A and some B. You'd add 5 this time on each side. So you have here n plus 1. On the other side, you take it common with B. So 5 into B plus 1. So we had to use strong induction, and you could have either used n minus 3 or n minus 4. But there's definitely a restriction on this n minus 3 and this n minus 4. Like the n you choose here, like n minus 3 has to be greater than or equal to 12. So n in this case has to be, for example, greater than 15. You can't choose here n to be 12 because then n 12 minus 3, that's 9. And remember, our condition is that it's greater than or equal to 12. This is why we did a bunch of base cases. Like we proved it for n is 12, 13, 14, 15. Like this wasn't a coincidence. We did this many so that when we do the P of n minus 3, like when we want to do it for 16, we're going back 1, 2, 3, like this. Or if you want to go back to P of n minus 4, you go to 12. Okay. So that's your first taste of strong induction. Any questions before we move on? Okay, good. I think I have like 3 more questions. I'm gonna solve all of them. If you need to leave at any point, please do. And I think the rest of the questions are still gonna be strong induction. So let's get a different taste of strong induction. In this one, just have this as a remark. In this one, what did we need? We wanted to prove P of n plus 1. We had to go, yeah, of course, they're gonna be recorded. We had to go back to P of n minus 3. or go back to P of n minus 4. So think of it as a sliding window. Whenever you had to prove something, you could either rely on something that was this back or this back. Okay, so now this goes back to this or to whatever was next, like a sliding window. Here it's going to be different. Here we're probably going to need everything. Let's see how. NIM is a family of games played by 2 players. The game is set up with several piles of stones. 2 players take turns removing the stones from the piles, such that more involving winner of the game who removes the last stone from play. Okay, so this is the question here. Consider games of NIM which begins with 2 piles with an equal number of stones. So imagine you have 2 piles, and they each have the same number of stones. Okay. Use induction to show that the player who plays second can always win such a game. Now remember, what's the game? Player 1 removes some stones from this pile. Then player 2 removes something from either this pile or this pile. They can choose whatever pile they want, and they can remove some number of stones from it. They're saying that the player that plays second can always come up with some strategy such that they always win. Okay. Use induction to show that the player who plays second can always win such a game. Okay. Just focus with me and try to absorb as much as you can. Base case. What if we only had 1 stone? Like n is 1. There was only 1 stone in each pile. Well, player 1 would take this stone, then player 2 takes this stone. There are no longer any stones in the game, and player 2 wins. Because remember, the player that takes the last stone or removes the last amount is the one that wins. So when you only have 1 stone in each pile, it's pretty simple, right? Player 1 has to remove one of them, then player 2 removes the other one. Done. Inductive step or inductive hypotheses. Assume P of n is true up to n. So for whatever number of stones that's less than n you have here or here, player 2 will always win. Okay, that's our assumption. Now we want to prove it for the inductive step. Thought I added something here. Keep. Okay. Okay, so now inductive step. And here's our winning strategy. We want to prove P of n plus 1, right? So now we have n plus 1 here, n plus 1. Remember, what does our hypothesis say? For anything between 1 and n, it'll work. We will now prove, hey, if it was n plus 1, it'll also work. Okay, so what's the winning strategy to do here? If player 1 removes some number of stones I from this pile or this pile, so without loss of generality, let's say he removed I stones from pile 1. Okay, so player 1 removes I stones from pile 1. Well, what should player 2 now do? He or she are also gonna remove I stones from the other pile. So from pile 1, sorry, 2. But what happens now? We are left with this pile has n plus 1 minus I stones, and this pile also has n plus 1 minus I stones. But this is included between n and 1. Because I has to be positive, they have to remove some number of stones. If they at least remove one stone, they're back into this range. Then done. Then player 2 eventually wins because of hypotheses. Because of our hypothesis which says, hey, if the number of stones is between 1 and n, then player 2 wins. Is it kind of clear? So the winning strategy, what we had to do here was whatever player 1 does, whatever they remove, we do the opposite. We do the same, we remove the same amount, but from the opposite pile. Okay. Let's recap this. So our game was, if we have the same number of stones in 2 piles, and in turn, the 2 players are going to be removing whatever number of stones they want from one of those piles, then we can say that player 2 can come up with a strategy where he always wins, he or she. So base case, if n was 1, that's easy enough. Just one stone here, one stone here. Whatever the first player removes, the other players removes the other one, they win because they were the last one to remove a stone. Induction hypothesis, assume it's true up to n. So whatever pile that you have that's less than n stones, player 2 wins here. Okay, now when we wanted to prove it for n plus 1, we simply said, from whatever player 1 removes I stones, player 2 removes the same amount from the other pile. But that means it's like now we have a new game where we have the same number of stones, but it's within the range of our hypothesis. So we can assume that player 2. And that's for here. So this is done, it's over. But these sort of NIM games, they're repetitive. Like you can find a bunch of questions and they all usually mean the same thing. So for example, here, it's the same question, but instead of piles of stone, we're saying 2 piles of matches. And again, they're saying the person who removes the last match is the person that wins. But here we're saying if here they gave you like the winning strategy, or not. They gave you, again, the claim. If 2 piles contain the same number of matches at the start of the game, second player wins. Here they actually tell you what you should do. Suppose your opponent removes m matches from one pile, you remove m matches from the other pile. So on your own, you can try to like reimagine this problem in a different way. It's the exact same thing, but here we're saying piles of matches instead of piles of sum. So you can solve a million induction questions, you're still gonna find something that's either similar like this or something entirely new. The more problem you solve, the better you'll be. Moving on. So strong induction. So we have the following. Every positive integer that's greater than or equal to 2 can be expressed as the product of one or more prime numbers. Prove that this is true. So what are we saying? You have some number n, you can write it in the form of prime 1 times prime 2 times prime 3, and so on. So how can we do this? Well, keep going with how you usually do. While you're thinking of the question, like if you're solving an exam, it's usually good to just write the base case and let your subconscious do the thinking. So base case, we have, well, n greater than or equal to 2. So start with n is 2. It's a prime number, so you're done. If n is 2, it's already done. It's a multiple of primes since itself is prime. Then you have n is 3. Might also be considered a prime, so also done. N is 4. 2 times 2, done. Done. So what this tells us is when a number is a prime, like it's already done. But what if it's not a prime? We're breaking it down, like 4, 2 times 2, 3, we break it down into primes. Okay, you can pause here and try to think of it. So inductive hypotheses assume, like if this whole thing is ready, P of n, assume true up to n. Let's now do P of n plus 1. So is n plus 1 a prime number? Or can it be expressed as a multiple of prime number? Two things, like we said before. N plus 1 is either going to be a prime or not. If it's a prime, then done. Just like 2, 3, 5, done. Otherwise, what does it mean that it's not prime? Then it has to be divisible by something, right? It has to be a composite. Well, since n plus 1 is a composite, then n plus 1 is going to equals a times b for some a and b that are less than n plus 1 and greater than equal to 2. You could have said 1, but it doesn't make sense 1. It's like you're saying it's divisible by 1, obviously. What does this mean? Then a and b have to be between 2 and n. So we're back in our hypothesis range. We broke down n plus 1 into a and b. Now a and b don't have to be prime, but they are within the range of our hypotheses. So using strong induction, using our hypotheses, a and b can be broken down into products of primes. So a can equal like p1, 1 times, or let's say p So A is PA1. Bunch of primes. And B the same thing. All the way up to PBI. So all you have to do is substitute A and B in here, and it's done. Okay. Moving on. Oh, I just realized that we also have another problem. Okay. So let A0 be 1, AN be this. Prove we have AN equals 2 power n minus 1. Okay. Well, again, base case. You can just pause the video and try to solve it right away. There's no hints here. It's simple enough. Except it's probably you ask yourself if you're gonna need strong or simple induction while solving this. So base case, A for n equals 0, or no, it has to be n is 1. Well, A of 1, what does it equal? 2 power 1 minus 1. So that's 1 over the side. Does it equal the same for this format? So summation from I is 0 to 0 for AI. Sort of like saying just A0, which is given 1, so that's done for the base case. Inductive step, it's true for n. I think we only gonna need n. Prove for n plus 1. So summation from I0 to n plus, so it was n minus 1. When you say n plus 1, it's like instead of n, you write n plus 1. Then minus 1, it's just going to be n. So we want to prove what this, if this summation, does it equal, same thing, 2 power n minus 1, but you write n plus 1 instead of the n, you're going to get n. So does it equal this? Well, AI. We can break this summation into two different parts. Same as the first exercise, I want to see my given. What does my given say? Summation of from I equals 0 to n minus 1 of AI, it equals 2 power n minus 1. So I want to see this range in what I'm trying to solve. So I have it from I equals 0 to n. Simply break it down. So from I equals 0 to n minus 1 plus AI plus summation from I equals n to I equals till n of AI. What's the first thing saying? This is my given. This is simply a n, right? From I equals 0 to n minus 1, right here. It's a n. What's the second thing saying? It's also a n. Summing from n up till n is just going to be n. But using my hypotheses, I know that an is 2 power n minus 1. And I have two of those. So it's like 2 times 2 power n minus 1. So done. We get, let me actually write it. It's pretty scribbly over there. It equals 2 power n. Yeah, so we don't need strong induction. Like I said, usually it's gonna be mentioned if it's strong or simple. If not, usually how I go with it, I solve it as if I'm solving a simple induction. And if I feel, oh, I need it to be strong, I simply go back and just say up to n instead of 4n, if you need it to be strong induction. Last question. Prove by induction that if a set S contains n elements, where n is greater than or equal to 0, then its power set contains 2 power n elements. So we know this. We know that if a set, its size is n, we already know that its power set, the size of that, is going to be 2 power n. But here we want to actually prove it using induction. Okay? Pause and try to think about it. It's also probably going to be simple induction. Do what I said, solve it using simple induction. If you need the strong, go back and scribble that for. So, base case. N is greater than or equal to 0, so hey, let n equals 0. That means S is just phi. Well, what's the power set of phi? Just the set containing phi. So is it true for the base case? Yes, because the size of this is just one element, which is 2 power 0. Like 2 power, what we had here. So it works for the base case. Our hypothesis is going to say for whatever, like up to n, oh, not yet, let's say for n, if you have some set that has n elements, then yes, its power set is going to be 2 power n. So if this, then the size of the power set is 2 power n. Proving for the step. Well, for n plus 1, we want to prove it, right? But what does it mean having n plus 1? Okay. So it's like before you had the set S, it only had n1, n2, or I'd like to write it as e1 for element, e1, e2 up to en. We had n elements. And we know that the size of the power set is gonna be 2 power n. Now we're saying you have a new set. Let's say it has all these same elements, but we added a new element, n plus 1, let's say. How can we prove that the size of S1 is now gonna be 2 power n plus 1? Well, it's like the same set, assuming, but the difference now you added a new element. So what are all the possibilities? It's as if you had every other, so P of S, you had all those possibilities. E1, E2, E1 and E2 somewhere, everything. The only difference now that we added a new element is that all of these subsets can either have this element with them or without them. So the size of P of S1 It's all those previous sets that we already had and all of those sets with the new element. So also it's going to be another 2 of n. Wrap your head around that for a moment. So 2 of these, you get, whoops, 2 times themselves is just 2n plus 1. Again, all of these sets, they didn't have the new element. So if you simply add to each of them the new element, you're done. Like for example, phi, when we add to it this new element, then we have the singleton that has the element e of n plus 1. When each of the single sets, you add to them e of n plus 1, you now have all the sets, or all the couple sets that have e of n plus 1. Same thing for the tuples, for the quadruples, and so on. By simply adding e of n plus 1 to each set you have, you're gonna then get the whole power set. So simply, the power set of S1, which is n plus 1 elements, is gonna be the previous set plus all the subsets of the previous set having the element n plus 1. Okay, now remember, what they didn't have to be the same elements. We just assumed they were to make it easier. Like these don't have to be necessarily the same elements, because the hypothesis says for any n elements, and your proof is going to be also for any n plus 1 elements. These don't have to be the same, but it still works even if they weren't the same, because you'd simply say for S1, assume you don't have one of the elements. So this falls back into your hypotheses, which is n, and everything we said. Okay, so we didn't need strong induction here either. And this was sort of different than the previous induction questions. This had like more explaining with English words, let's say, than actual stuff like this, mathematical. So be careful, be prepared for any front. Okay, I think that's it, everything I want to mention. Okay. Thanks, Samer, my lone survivor. See you next time. Okay. Again, if you're watching, make sure you practice everything, the functions, the sets, the cardinality, the inductions before Monday. So you can, so your exam is probably gonna be Tuesday, so that's like the last day, the last chance to really ask if you have anything that's not there. So good luck and see you next time.